wanted to take an opportunity to inject some newer ideas. So a lot of the charts I brought in were from the 2005, 1995, 2000, and I'm working on a project called Clario at NASA that we started in 2011, and we're hoping now to have a mission to the International Space Station. We'll see if we can get them just shortly after history. That we'll be doing climate type measurements. So I want to spend a little bit of time talking about it because it has to do with error budgets, and it has to do with maybe we can improve our reflected space calibration because of this high quality type of measurement that might be available. So the inclusion of the metrology community has been enormously helpful to remote sensing, and it's going to continue. And it's something that has to happen if we're going to do climate level measurements. And what I had talked about a little bit ago was using detectors. I wasn't sure if someone was coming back in. But trying to basically get to where we have a better way to calibrate instruments in general. And the way we started doing is something called Circus, which was a NIST-based activity. National Physical Laboratory has a similar system. And instead of using broadband light, it uses lasers, tunable lasers basically. Now the problem is still understanding what the output of that tunable laser is. And what you do is you build radiometers that are really well calibrated. And so we can go to a national lab and they have a cryogenic radiometer that will look at a laser and measure the output of that laser perfectly. We're talking like 0.03% type of absolute uncertainty. You move that laser a little bit and you have your radiometer look at that. And this radiometer moves much better than a lamp does. So it will maintain its calibration and can now go into another facility and calibrate a source. And then that source can be used to calibrate a radiometer. So what this means is we now have the capability to calibrate systems that are going to space to better than 0.2% absolute at 2 sigma. But this says K equals 3, so that would be 3 sigma. But to a very high reliability, we can have a number that's absolute to 0.2%. That's a factor of 10 better than anything else we have right now. So this is what's going to allow us to start doing climate quality type work from space. And that's been what's proposed by Truce and by Clario. Now, Truce is the one that Nigel Fox has put together, and he's been pushing. I was part of his team back in, I think it was 2003, maybe even before that. And the idea is in Clario, it's a similar type thing, except Clario, we have infrared, we have reflected solar, we have GPS systems that can get us information about the temperature of the atmosphere and the top of atmosphere reflectors. Nigel's, the Truce instrument is just in the reflected solar. Not just, but it covers only the reflected solar part of the spectrum. But the idea is that you're launching systems that are so well calibrated that you know they're getting the right answer, which is why I love Nigel's name of Truce. He's launching it to measure the truth. And as close as we can, factor of 10 better than what we do right now. So Clario, I'll talk a little bit more about it. The whole idea is that it's called Climate Absolute Radiance and Refractivity Observatory. The absolute accuracy right now is what stops us from getting information about climate change. That we cannot tell the difference, I have another chart to show this, we cannot tell the difference between a natural change and a real change that was caused by something else. All right? Climate model predictors are being used now to start to make societal choices and decisions for humanity, and those models need to be improved. And the whole idea is that right now, if you have a differing values amount of carbon dioxide doubling or some other amount, and different models, these models disagree with each other going out into long time periods. And the uncertainties between them, there's still a lot of, okay, which one's the right one? And the ice caps don't know the difference of which model is right or wrong. They just know that if it goes over 0 degrees Celsius, they're not going to be ice. flows anymore, they're going to turn into water. And that's a big problem. So the whole idea is that we have to make these measurements from space. We were in the first decadal survey as a tier 1. Got put sort of in the background. Now we're going to space station for a small little Pathfinder mission. And then the hope is that will then convince people that we should have a real mission to do the real measurements. As part of that, there's a reflected solar instrument. And when we designed the full-up instrument package, we came up with what we call a 2-box model. And these are standard imaging spectrometers. They're off-road designs. We put in the mechanical part of it in a way that they are very thermally stable. Both the temperature, they're stabilized, as well as all of them are the same metal, so that if there is a change in the temperature, everything moves together the same way. And we went with 2 boxes because we're using gratings. And so it was much easier for us to control the stray light if we went from, in the case of 1 box, which we call the blue box, it went from 320 nanometers to 640 nanometers. And then our red box went from 600 nanometers to 2400 nanometers, 2400. So we covered 2 orders with the shortwave infrared, and we'll cover a single order with the blue box, which then makes it a lot easier to get rid of the secondary orders in the scattering process. The novel idea is we're using the sun as a calibration source. TRUCE does the same thing through a different pathway, but the idea is that you turn your instrument and you look at the sun. And then you turn and you look at the ground. Well, those are the 2. That's the incident light, there's the reflective light. The ratio of those 2, if the instrument did not change, is the reflectance. Now, there's just this one little minor detail. The sun is about a ½ degree in size and is 50,000 times brighter than the object you're looking at, the Earth, which is 110 degrees in size. So we just have to account for little minor differences in geometry. And oh yes, we have to do them at like the 0.005% level of uncertainty in terms of your aperture sizing. But those are little minor details that will be worked out, I'm certain. We're getting help from NIST and from other groups to do it. But what's interesting for our community and the calibration community is now you have something up in space that is, as weird as we can call it, perfectly calibrated. The climate folks are happy about that because we can set up Clario and we can go into what we call a perfect polar orbit. It's not inclined at all. It's actually a 90-degree orbit going directly over the poles. And now that precesses under the Earth, or over the Earth as the Earth precesses underneath it. So you basically get global sampling over a full year, but it's at different times of day. So we're basically getting a global measurement of reflectance at a variety of different times, and all of that gets averaged together to come up with single numbers on a monthly scale, on a weekly scale, and across the globe and across latitudinal bands. We're worried that that sampling is not going to be good enough. So if we can calibrate other systems like a VIIRS or a MODIS that are in a typical sun-synchronous orbit, so they're covering larger swaths of ground in shorter time periods, but they're all at the same time of day, and we get the same answer with that sampling as we do with the other sampling with the precessing orbit, then we have confidence we're getting the right answer. And the way to do that is we take the perfect instrument and we cross-calibrate it to the other one. And so this is the same approach everybody's been using, the simultaneous data overpass that you do near the poles, and you have 2 systems that come over, and they're both looking down, and you say, okay, they're looking down at the same time, same place, we're calibrating. Clario is going to be put on a 2-axis gimbal. So as we're starting to cross another satellite anywhere in the orbits, we can go and we can turn and twist and track that satellite's view. So we'll get, instead of maybe 10 or 20 simultaneous data overpasses and only at the poles, we're going to get a couple hundred opportunities at a variety of different sites, a variety of different spectral location or spectral values, brightness levels. We'll even get, in the case of MODIS and VIIRS, at different scan angles for those instruments, which allows us to then assess their polarization, sensitivity, and degradation as a function of scan rate.
That'll be on the space station or in the
real one. The space station, we're limited in. We can't get the full 2-axis, and even if we did have the full 2-axis, we would be blocked by some of the structures. We're having enough trouble getting away to the point of the sun right now. So we picked out where we want to be on station to be able to do that, because we want to do that methodology. And we still have enough to do about, I think it's a third of the opportunities of cross calibrations. But the advantage is now we have a way to cross-calibrate these other instruments. The advantage then for me in reflected space calibration is not only do I have a Clario system that I can use to look at the test sites that I'm using for calibration, and I can predict my radiance for Clario and see if I'm even close, I can also then do it to the other ones, like Veers and Modus, and see what kind of numbers I get with them. Because now they've technically been calibrated to a much better scale than they are right now.
Excuse me. Is there any possibility to increase the monthly uncertainty in the launch time or POD? Because it's a small number.
To increase the
uncertainty, because the degradation of the optics in the calibration system.
so your worry is so I'm saying I can do this to 0.3%, and you're wondering if that's going to be 0.3% throughout the whole lifetime. And the answer is yes, because when we look at the sun, we will calibrate every time. So if there is a sensor degradation, that calibration against the sun will automatically remove that degradation. The problem is, because we have a 50,000 time difference between the Earth and the sun, we have to attenuate it in some fashion. And we're using pinholes and neutral density filters. So transmissive filters and pinholes. Those might change. That's where the moon helps. So we use the moon as purely a stability, not as an absolute calibration. We look at the moon once, and then we look at it again 2 or 3 weeks later, a month later, and we keep doing that. And when we look at the moon, we do not need those attenuators. So if the sensor shows no degradation looking at the moon, but shows degradation looking at the sun, then we know it's the attenuators that are the problem, and we have to change our error budget and do a recalibration. But if they both show the same degradation, then we're confident that it's the detector package, and that gets taken into account, and then we look at the Earth and do the ratio. The ratio gets rid of that degradation. So we should be 0.3% end of life.
Is it a mechanical rotation, or do you have multiple slots basically that you would open and close to?
For the attenuators,
No. So to look at the sun, the Earth, and the moon, is it actually rotating?
it turns the whole instrument, because one of the difficulties with systems like you described is you need a mirror. So that mirror can degrade. If there are ways that we could have, we looked at the design and it turned out the size got too large to have a mirror that would rotate that up. The angle was the same for no matter where we were. And so it was much better just to turn the whole system to do that.
Follow-up question, and feel free not to answer this one, but redundancy is a big thing. So I assume it's all space work and all that, obviously, but what level of redundancy are you putting into the system so if something fails, it'll still work?
Almost none. For the station version, 0.
Sure.
For a real version, your redundancy would be, I think the only redundancy we had, I can't remember now. None. The electronics, you can have redundancy in that. That's pretty straightforward. But detector packages, you typically don't do that. The attenuator, what you do is you basically design it so that it will fail gracefully. And so you don't want it to fail, and it's kind of a pinhole, you want it to snap back. And so there's ways that you build it, either with explosive bolts or it's in pressure so that it will release and snap back to where it was before. Because we went through the quality mission assurance, and I'll have to double check, that's a good question, but to my recollection, there's not something that you and I would recognize as a key piece that's redundant. You get buried in the weeds of what these guys do for a living on space-based missions, and okay, yay, you're redundant there, but it's not like my filter wheel, and it's not like the pointing mechanism, it's not the detector package. But it's known that, so for instance, these arrays that we're using for the detectors, if a detector fails, you just do not get those data for the rest of the mission. That's life. We do our best to find systems that are robust enough to meet our mission lifetime requirements.
What is that number, like mission lifetime, both for the space station and
The station, officially it's a 1 year. So we're hoping to get more than that, but 1 year is all we're supposed to get. On this one, we were going to launch 2 separate platforms. We need 5 years of data, and it was cheaper, instead of trying to get a 5-year kind of Class A mission, it was cheaper to get 2 Class B platforms built and launch them and have them specified at 3 years. Because if you build a 3-year mission, then there's a probability it'll go longer than 3. But if you have 2 3 years together and they're launched at appropriate timing, then you're guaranteed to have, by their statistics, you're guaranteed to have a 5-year mission. The reason I liked working on Clario was it was the first project I worked on when I went to NASA, and it was done right. So it's ruined every other project for me at NASA. Because most times when you develop requirements, the answer is, well, you guys can do 3%. Let's just do 3%. There's not a, well, here's what I want to measure at the ground. So I want to be able to count leaves. And in order to count leaves, I have to have a spatial resolution of 3 meters, and I need to have a band at 485 nanometers, and I need to have a radiometric resolution, or a DN, I need a 12-bit system, and it needs to be calibrated to better than 0.5% relative and 3% absolute. That never happens. They've not figured out through all of the codes and the processing what the instrument needs to look like from space. It's, what can you give me? For Clario, we went through the process of, all right, you climate modelers, what are you doing? And what are you trying to find? What's the needle in the haystack? How big is the needle? How large is the haystack? And how good of a measurement do we have to make in order to try and detect? In our case, we were trying to detect a real change above natural variability. So on any given year, if we take a measurement of the reflectance or the temperature of the Earth, we're going to get a number. And I can make a measurement next year. And there's a chance it will go up or down simply because of El Nino events, quasi-biennial oscillations, polar vortexes. You come up with something and they've got a name for it, and it's going to cause wiggles. And over time you start to get trends. And so it goes back to my sampling question of, well, how many data points do I need with my vicarious calibration at this level of precision in order to say trend, no trend? This is how many observations do we need over what length of time at what level of accuracy in order to say trend, no trend, above what we think is normal, natural, just bouncing around because Earth is being Earth. And what they did was in terms of this is now the trend accuracy, and we opted for trying to get to where we were looking for 100% cloud feedback equivalency. So if the clouds in the atmosphere change, you get 100% effect because of that decadal change, and it was due to anthropogenic forces. We have a prediction of what we think man's influence will have in terms of the cloud reaction in the atmosphere. So here was what would happen, is this kind of like, you have to have something below that in order to be confident that you're going ahead and you know it's a real change. If you want to do it at 95% confidence interval for a 50% cloud feedback, here's the line you have to get to. So the tougher the problem, the better you have to make measurements. And then along here is the length of time that you have to make the measurements, and each of these curves is for a different level of absolute accuracy. This is absolute SI traceable, demonstrated, proven accuracy, absolute uncertainty, sorry. The orange line here, that's 3.6% absolute uncertainty, K equals 2 of MODIS. So we would need more than we would almost need 40 years worth of data to basically have a record that, if that record showed a trend above a certain amount, we would say with confidence, this is real. So all we have to do is keep the MODIS record going for another 23 years or so. That's all. And then we'll be in good shape. Oh, and by the way, the calibration can't change between now and then. We still have to maintain 2.6%. And it has to be all that great. As you start to improve the accuracy, then that time to detect gets much shorter. If you had a perfect system, you launched a 0% uncertainty instrument. The Earth itself will still force you to have to wait about 12 to 15 years to see the trends we're talking about and be confident that is a real trend. This is why this is starting to get really important, because we're starting to admit to ourselves that there's probably something going on with the Earth. We should have made the measurements 10 years ago to be able to say, yes, it is. But we've been arguing over that we've been arguing over the 20 years. No, there's no reason to make measurements anymore. We don't even need a measurement. This is pretty clear that we ought to be at least getting a measurement. And let's get it in the ground, mark it and say that's our measurement, and then if we have to wait, if we do true SI traceability, we can go wait 10 years and put something else up. We might be able to do combinations of MODIS, especially if we can get VIIRS onto the same scale as Pathfinder, and then we can cross-calibrate MODIS using VIIRS and go back in time. We at least might be somewhere in this range that we can prove to some people that, especially if the trend is large enough, this is a real trend. Right now, the trends we're seeing with MODIS just aren't that large, and it's still within the natural variability. So that 0.3% in reflectance has a basis in reality. It's not just a number the group came up with. This is a real 0.3% that we have to get to. It's not quite perfect, but it was the number that was reasonable that got us really close to a perfect observing system. So how does that help this? We've been talking reflectance-based calibration the whole time. And the way I like it is, if I get truce or I get Clario, now I have the right answer. I can start figuring out which one of these is the right instrument. And if I know which one of those is the right instrument, I can start going, okay, why do the other ones not agree with this? They should. And hopefully it'll be because their calibrations are off. Because I can look at Clario and say, oh, well, they need to be recalibrated because they're not right. But if it turns out that Clario thinks they're the right calibration, and I get these kind of differences at a test site, then I can look at what's the difference between the blue and the orange. I can look at ETM Plus and Aster and start to say, what's different about them? Well, one's whisk broom, one's push broom. Maybe ETM Plus has something that's related to a scanning system. My sight's not quite as uniform as I thought. I'm getting effects because we're scanning in optics. These are the questions I cannot even consider at this point because I really do not even know if these are real differences. Why would that Hyperion system have a larger standard deviation than the others? I know it's SNR, I know it's low signal noise. Everyone I show this to says, no, it's your data because you have the atmosphere. It drives me, it should drive you crazy as well. It makes me just almost angry. But if we get something like a Clario, then I can prove to them and say, no, the method is right. And it goes down to this triangle that I've used multiple times for many, many years. I started when I was teaching. And it's the idea that I have sensor, measurements, and processing. So in the reflectance-based approach, I have my measurements, I have the sensor I'm trying to calibrate, and I have my processing speed. And we're stuck basically going back and forth between this because the sensors do not provide me any feedback on what is the right approach. We think we have a 2% uncertainty because of panel VRF. We'll never be able to prove that it is better or worse because of the fact that I don't have a sensor that's better than that can tell me that measurement was wrong, that measurement was right. And so the goal of getting something like Clario Truce up there is it's going to help a lot of other processes that we don't even think about right now because you'll know that there's an answer out there that has to be the right answer, and it makes you try to fix your processing or your measurements to make it match. So Truce and Clario let you get closer to the truth. So if you were here on Tuesday, you saw this already. But the idea is I just, on a spreadsheet, just took a normal distribution, created 2 scattered plots of data, one that had a mean and a standard deviation, where the standard deviation is smaller down here, but it differs more from the absolute answer. And then up here, I'm closer in terms of the measurement, and I have a lot of scatter. This is what Clario and Truths are really going to try and do. We're going to try and get really right on top of this correct answer with a lot of scatter. We don't care about the signal noise because we're going to average spatially, we're going to average temporally, we're going to average spectrally. And by doing that, we're going to drive down our scatter to where our final product is going to be a tiny little dot around that square. What I asked on Tuesday is to get people to think which is the better data set. And it depends. Depends on what you want to do. Right now, with reflected space processing, I'm trying to get to this lower left. Because right now, we think we're in the upper right. We think that we're pretty close. We have a 2.5% absolute, but I also have a 2.5% standard deviation. So it's really difficult to make any conclusions about how good I'm doing. If I can shrink that, I would even be happy to find out that my 2.5% estimated bias is wrong. I would be ecstatic to finally learn that and have to fix something because there's a bias that we finally teased out because we have much better repeatability. Clario and Truths will help us do that. It'll help us get rid of some of the scatter, it'll help us shrink that down. It'll also help us figure out what the right answer is and get rid of some of these biases that we're creeping into our measurements. So cross-calibration with test sites, cross-calibration with other instruments. What I'm hoping will happen is we'll get such good data, we could model like a railroad valley. I can get the BRDF almost perfectly from space. And then that can feed into a physical model for the site that maybe I don't even, all I need is the relative measurements I'm making up there right now automatically, and that can then be fed into a model which is predictive as to what the radiance is off the top of the atmosphere.